Hello, good afternoon everyone. Myself Yuvas Prabhu, student of Namchi Government College. We are in roll number 18NS0034. Before proceeding to my topic, I would like to thank our respected teacher, Sir Dr. C.P. Khatiwada, Namchi Government College, Department of Physics and Sikkim University for providing us such a golden opportunity to make a video on the partial fulfillment of our BSc Physics Honors Session 2021. So, my topic is linear harmonic oscillator. So, linear harmonic oscillator, there are two basic concepts: quantum concept and classical concept. Quantum concept, we deal with Schrodinger equation and Hamiltonian equation, and the classical concept, we deal with Lagrangian equation of motion. So, in quantum concept, we have a very long derivation. So basically today I'll be dealing with classical concept, that is using Lagrangian equation of motion. So for the next I will be explaining in quantum concept, simple definition and giving equation.
Start.
So quantum concept. So what quantum concept defines linear harmonic oscillator is that linear harmonic oscillator describes vibration in molecules and their counterparts in solids, the phonons. The linear harmonic oscillator, even though it may represent rather non-elementary objects like a solid and molecules, provides a window into the most elementary structure of the physical world. So, this is the definition of quantum concept of linear harmonic oscillator. So now the main two equations that describes quantum concept of linear harmonic oscillator I'll be explaining in next.
Start.
So quantum concept. So in quantum concept, the linear harmonic oscillator is described by the Schrodinger equation. So Schrodinger equation gives I h cut of del superlative of t psi bracket of x t equals to h cap of psi x t. So this is the Schrodinger equation which describes the quantum concept of linear harmonic oscillator. Similarly, for Hamiltonian equation gives h cap equals to minus of h cot square by 2m del square upon del x square plus of half m omega square x square. So these are the two equations which describes linear harmonic oscillator in quantum concept. So basically this equation comprises one of the most important examples of elementary quantum mechanics. There are several reasons for its pivotal role. The linear harmonic oscillator describes vibration in molecules and their counterparts in solids, the phonons. Many more physical systems can be at least approximately be described in terms of their harmonic oscillators models. The most eminent of this oscillator is linkage to the boson, one of the conceptual building blocks of the microscopic physics. Example, boson describes the models of the elementary electromagnetic field. So now, in the next session, I'll be dealing with the physical concept or the classical concept of linear harmonic oscillator.
Start.
So in the previous section, I was talking about the quantum concept of linear harmonic oscillator. So in this section, classical interpretation of linear harmonic oscillator. So what linear harmonic oscillator in classical concept is that a linear harmonic oscillator consists of particles acted upon by a force whose magnitude changes linearly with distance x from mean position. It oscillates along a straight line about a fixed point known as its mean position. So this is the definition of linear harmonic oscillator in classical concept. So now in the next session I'll be deriving equation using Lagrangian equation about the classical interpretation of linear harmonic oscillator.
Start.
So in the last session, we were talking about the definition of linear harmonic oscillator. So here is a small figure I've drawn. So this is this is an object which is dash dotted line is its mean position. So x is distance between these two lines. So this is a spring. So whenever we apply a force in this initial object, it will displace in this section. So this is force. So after applying force, it will again restore. It will gain or restoring force. So after that, it will come again to its original position. So the restoring force acting on linear harmonic oscillator is given by F is proportional to X, which is also called Hooke's law. We know that force is directly proportional to the X, that means distance. So we are simplifying this equation, we get F is equals to minus of Kx. So here we have minus as well as K. So here negative sign means the restoring force always acts upon opposite sides. That's why the sign is negative, and the K is here is the spring constant. So now using Lagrangian equation, we will be solving linear harmonic oscillator. So Lagrangian equation, we have d by dt curly L by curly x dot minus of curly L by curly x equals to 0. So now in this Lagrangian equation, we have to find here is its kinetic energy as well as its potential energy, and we have to substitute in this equation, and we will find a linear harmonic oscillator in classical concept.